Okay, so this lecture will look at ring compounds and their conformations, so their three-dimensional shape. So many organic compounds have rings in them. Some rings are more stable than others, and the stability of the ring depends on a lot of things. It depends on how big the ring is, what is attached to the ring, how many things are attached to the ring, and the overall three-dimensional shape of the ring. So we'll just look at three-membered rings, so cyclopentane epoxides, for example, four-membered rings, five-membered rings, and six-membered rings. But you can have, rings can be bigger, 7, 8, 9 carbons in a ring. But the most common by far are 5 and 6-membered rings. So if we take a three-membered ring, so if I took a model set, and if I wanted to make a three-membered ring out of it, it's kind of hard to see, but if you wanted to make that into a three-membered ring, it's really difficult. You can see the bonds here starting to break because three-membered rings are difficult to make because they're very highly strained. So if we had a three-membered ring, I could draw better than that. Like cyclopropane. So if you remember your geometry, what does the bond angles have to be in a cyclopropane? So of course each of these carbons has 2 hydrogens on it. So the bond angles have to be 60 degrees. That would be an equilateral triangle, for example. And so of course 3 points define a plane. So three-membered rings have to be planar. The geometry determines that, dictates that. So they have to be 60-degree bond angles. But that's what's a hybridization of that carbon. So the carbon's got 2 hydrogens and 2 other carbons attached to it. So it's got 4 things attached. So it's sp3 hybridized. And if it's sp3 hybridized, what does the bond angles want to be? They want to be 109.5 degree bond angles, but they're forced to be 60-degree bond angles. So three-membered rings are very unstable. One, because they have angle strain. All right, they want to have 109.5 degree bond angles, but they're forced to have 60-degree bond angles. And they're also very unstable because, let's see, what's called torsional strain. So what is torsional strain? So if this is forced to be planar, then if we took any of these, get out of the way, any of these 2 hydrogens have to be right behind each other because the molecule has to be planar. So that would be what's called torsional strain. That's a steric interaction. So all of these hydrogens are eclipsed. So it doesn't matter if it's an epoxide, three-membered ring, or cyclopropane, four-membered ring. So if you remember what epoxides are, it's an oxygen and a three-membered ring with 2 carbons. It would have to be planar as well, and 4 hydrogens, 2 hydrogens on 2 of the hydrogens on each carbon will have to be eclipsed with each other. So in general, you can make three-membered rings, but they're not easy to make because of the angle strain and torsional strain. Four-membered rings are more stable. They're easier to make. So I can build a model with a four-membered ring with my models, right, to make the cyclobutane. And so cyclobutanes, since they have more atoms, they don't have to be planar, and so what cyclobutane does is kind of puckers, makes a puckered shape like that. And so by puckering, so if it's planar, then you can see, like here, these hydrogens have to be right behind each other. But if it puckers a little bit, then you can see that the hydrogens are no longer directly right in front of each other. They're more staggered. And so that stabilizes the molecule a little bit. But it's still difficult to make four-membered rings, because if it's a four-membered ring, then what's the bond angle? So bond angle or around 90 degrees, so you still have some angle strain. But the puckered shape relieves some torsional strain. Okay, and then if we go to 5-membered rings, so 5-membered rings are extremely common in organic chemistry, and they are much, much more stable. Okay, so if we have a 5-membered ring, so what 5-membered rings do, so one of the carbon atoms is out of the ring, and it forms more like an envelope shape. And so by doing so, of course, you can see that if you look down any of these carbon-carbon bonds, then these hydrogens, this hydrogen on this carbon is setting between these two, so that relieves some of the steric strain. We're going to spend most of our time, so 5-membered rings very common and stable. They adopt an envelope shape. So let's take a little bit of time here to introduce a new concept. So what if we had two things on a cyclopentane? Could be a cyclopropane, cyclopentane, doesn't matter. But if we had two things on there, so if we attach two other things, so let's say the white represents hydrogen and the red represents anything else. Okay, so if we have that, so let's say the white is hydrogen and the red could be anything else. Maybe it's two methyls. So now there's two possible molecules that we could have. The two methyls could be on the same side of the molecule, like they're drawn here, and that would be what's called the cis isomer. Or if we take this one off and we take this one off, this hydrogen, and put this hydrogen down here. So you can see to do that I had to physically break bonds. I had to break atoms apart and then reform bonds, so the molecule can't do that by itself. So this is a totally different molecule. Molecules can't interconvert between each other. So here now we have one hydrogen on top of the plane of the ring, or one methyl on top and one methyl on bottom. So this would be, so if we drew that, so now we have a methyl on bottom. So one of the red balls on bottom, or one of the red atoms on bottom, and one on top. And so that would be what's called the trans isomer. So if the two things are on opposite sides of the ring, they're trans to each other. If the two things are on the same side of the ring, they are cis to each other. So that would be the cis isomer. So if this is a methyl and this is a methyl, so let's name these two molecules now. So the parent would be a 5-carbon ring, that would be cyclopentane, with the methyl on carbon 1 and the methyl on carbon 2. So this would be 1,2-dimethyl cyclopentane. But of course this one would be, so they're both 1,2-dimethyl cyclopentanes. But they're obviously not the same molecule, so they differ spatially, right? So what kind of isomers are they? If they differ spatially, they are stereoisomers. And so in order to distinguish between the two stereoisomers, we need to put the stereochemical designation, cis and trans, in the name. So, and that comes at the front of the name in parentheses. So this would be the cis 1,2-dimethyl cyclopentane, and this would be trans 1,2-dimethyl cyclopentane. So anytime you have this stereochemical designation for a molecule, and all we've covered is cis and trans so far, but there will be others. Those always come at the front of the name in parentheses. Okay, So let me move this down a little bit, so we'll take one or two more examples. Oops. Okay, so we could have had, a three-membered ring. So if we had a three-membered ring with two things attached, so maybe it's a chlorine bottom, so the dotted line means it's below the plane of the ring, and the solid wedge means it's above the plane of the ring. So if they're on opposite planes, if one's on dotted and one's on solid, then they're trans to each other. So this would be trans 1,2-dichloro cyclopropane. Or if we had this molecule, not drawn very pretty, but you can distinguish it hopefully. That would be 2-3 carbon chains attached to the ring, and they're not linear, they're branched, so that would be isopropyl groups. So this would be 1,3-di-isopropyl cyclobutane, and both of the isopropyls are on the solid wedge. So it doesn't matter if they're both on the top solid wedge or they're both on the bottom dashed wedge, they would be cis to each other. So this would be cis 1,2-diisopropyl cyclobutane. Okay.